These are some of the ways we can combine 4 elements in a group. Now, if it happens that in our system the binary operation is not associative, then there is no reason to believe that these elements are equal. In fact, you see, without even thinking, I took only 3 integers, and it turns out that this itself, there itself, the associativity fails. So you have every way of bracketing this product may give you a new element, and there is no apparent relationship between them. So what do? The theory becomes, the calculation loses naturality, and unnecessary complexity arises in this calculation. There are non-associative operations in mathematics which are studied. For example, you see here subtraction is non-associative, but still it is important for some purposes. But it makes things extra difficult if associativity is not there. So associativity is giving us a way of getting rid of brackets. There it is not necessary to keep track of the brackets if our operation is associative. We can get rid of these brackets because of associativity. This product will still make sense, because no matter how you decide to bracket, now for 3 elements these are the only 2 ways. For more than 3 elements the number of ways will be higher and higher, but the associative law allows you to get rid of brackets. Any way of bracketing this product gives you ultimately the same answer. So you can define g dot h dot k to be any one of these. Note that we have to define the meaning of this, because the binary operation is defined only for 2 elements. It's not defined at once for 3 elements. It's not a ternary operation. It's only a binary operation. So its meaning has to be defined. So unless associativity is there, you cannot define a product like this. So this is one advantage in a group. Then after that you have an identity element. It just is a fact in groups that there is an identity element, and every element has an inverse. Now there is one more thing that we should discuss at this point. You see, if you look at the definition that we have written down here, there exists an element, not the element, an element in G which acts in a certain way, that G dot E is equal to G is equal to E dot G for all G belonging to G. From the definition we don't know whether there may be more such elements. There may be, we don't know. So that's why in the definition we just require the existence of at least one identity. Okay. If one exists, then we say that G has an identity, and that element is called an identity. Just like that, for every element G in G, there exists an element G prime in G, such that G dot G prime is equal to E, which is equal to G prime dot G. Here also, for this G, G prime may not be the only such element. There may be more. Okay, and the definition does not require us to show that there is exactly one G prime. It just asks us to find at least one G prime. And if a G prime exists, we say that it's an inverse of the element G. Now, if a system satisfies these four properties, these four conditions, then we call it a group, and then we will prove it as a fact that in a group an identity element is unique, that is, there is exactly one identity element. If there is one, then there is only one. Also, for every element G, its inverse, actually there is only one inverse. That we will prove as a result, and then we can, after proving that uniqueness, we can give a symbol to it, and we will write G inverse. That will come afterwards. Okay. So let us now leave this discussion and go back to what is given in the text. So looking at the source of our definition, we can see that we already have examples of groups. Let us just write what is written in the text. Looking at the source of the above definition, it's clear that this is a group for any non-empty set S. So we already have many examples of interesting groups available to us. Right off the bat, right from the very beginning, these are many groups. These provide us with examples of groups. These are the examples of groups. I should not say the examples of groups, but these are they constitute a class of groups. You change the set S to be any non-empty set. You change S here, you are going to get more and more groups. Okay. In a sense, these groups constitute a universal family of groups. We will show in a section. We will get to that section. In what section exactly the section is not mentioned here, but there is a theorem due to mathematician Cayley, which says that whatever group you can come up with, that ultimately is either one of these or is inside one of these in some sense. We will see those things. Okay. Due to a result by Cayley. Okay. Now we come to one particular thing about these groups, one more aspect of these groups. Let me write it here, from here itself. In section 1.2, we also noted that if the set S has more than two elements, then there exists elements alpha and beta in A of S such that alpha composition beta is not equal to beta composition alpha. If you recall the end of section 1.2, there we actually proved that this is the case. If S has more than two elements, 3 or 4 elements, or even infinitely many elements, S, keep in mind that S just has to be a non-empty set. S should not be empty. Other than that, there is no restriction on S. S itself can be infinite. Then we can find at least two elements alpha and beta in A of S which behave like this. Alpha composition beta and beta composition alpha are not the same thing. Now this is somewhat counterintuitive as far as operations go. At a lower level, the operations that we came across, all of them satisfied this thing at least. All of them means the major ones which are the most important. They are not like this. For example, if you multiply 1 and 2, then the order does not matter. The result ultimately is, okay, let us take a non-trivial one, 3 times 2 and 2 times 3. Similarly, addition also is like that. Order of the summands does not matter. You can write them in any order. This operation, however, this composition of mappings is not like that. So this prompts us to single out a class of groups, and under that class there are very few groups as compared to the other groups which are like this, but still this special class of groups is very important. Those of you who are already familiar with these things, they will know that I am going to define abelian groups now. This prompts us to define a highly special but very important class of groups. So this is the definition. Let G be a group under the product dot. Instead of writing let G comma dot be a group, We also express that by writing like this: let G be a group under the product dot. Now you may say, why am I saying product? You may ask. We say product because this is a generic symbol for operation. Dot is not any particular binary operation, but it's just any binary operation. And since this dot looks like ordinary product of two numbers, so we call this product. It's just a way of saying, nothing else. Don't attach too much meaning to this word product in this context. It just says that it's the since some people find it cumbersome to write binary operation or operation. Product is much easier to, not write, it's not easier to write than operation, but it's easier to say, I think it's easier to say the word than operation. So let G be a group under the product dot. If A dot B, I think I need ink. Give me a moment. If A dot B is equal to B dot A for every pair of elements A and B in G, then we say that G is an abelian group or a commutative group. Okay. Commutative, we also say commutative group, but abelian group is more common. So from this condition that made us make this definition, we can see that groups which are not abelian are actually there, and as a continuation of that definition, well, I should not say as a continuation, but as a consequence of that definition, groups which are not abelian are called non-abelian or non-commutative. Note that this is, or let me write the actual notation, this is a non-abelian group if S has more than two elements. Because we have already proved these things. So this is the benefit of doing things in advance. We already have proved that all these are all groups for any S, and if S has more than two elements, then all of them are non-abelian. Okay. one more aspect of a, or rather I should say natural aspect of a group is the number of elements in it. In it means in the underlying set. For a group G, we denote this number by this symbol O of G. Note that this matches with our definition of order of elements in matches with the notation of order of elements in a set. If A is a set, at least when A is finite, then the number of elements in it has been defined by order of A. You need to recall this notation. You try to remember this formula that we have already proved. Number of elements in the union of two finite sets. And call this the order of the group. Now this number, if it is infinite, if the group has infinitely many elements, then well, it's infinite. But it is the most interesting when this number is finite, and surprisingly, a lot of the properties of a group depends only on this number, not on the group itself, but just the aspect, that number of elements. This number is the most interesting when it is finite. In this case, we say that G is a finite group. Otherwise, G is said to be an infinite group. Okay, so going back to our actual source of definition of groups, when let me write it in another paragraph. When S is a set having n elements where n is a positive integer, then A of S has n factorial elements, and we have actually proved this in section 1.2 itself. What is the, let me quickly go to the exercise number. So this is exercise 7 of section 1.2. There we have already proved that this number is n factorial, which after all is finite. No matter how large it is, that does not matter. Elements, and hence in this case A of S is a finite group. You see, it's do you see, here I am writing A of S is a finite group. I am not mentioning the operation because we know what the operation is. So that's why sometimes instead of writing the full notation, we just simply say that G is a group, is a finite group, and it has a name. It's called the symmetric group of degree n and will be denoted by the symbol Sn in our discussions. Okay, so that means although S can be any set, but sometimes it is finite also, it can be taken to be finite. If S has n elements, then our group has n factorial elements. Nonetheless, it's finite again. So, and it's called the symmetric group of degree n, and we will, instead of writing A of S, we will simply use this symbol S suffix n. So whenever we see Sn in our discussion on group theory, at least in this book, we will understand that it is the symmetric group of degree n. Now here there is a very subtle thing which Herstein has not said anything about. You see, what is the, and that subtle thing actually is there in this AS itself, but let us just not go to that general case. We look at Sn. You see, say n is 3, then if n is 3, then what are we doing? We have a set S which has 3 elements, say x1, x2, x3, and we are looking at A of S, means in A of S we will have all the bijections from S to itself. all the one-to-one mappings of S onto itself. Okay, and there is of course composition of mappings and it forms a group. If you have a different set S prime also with 3 elements, to make the things more concrete, let me, instead of taking abstract elements, let me actually take some, say, -1, 0, 1, these 3 integers, and in place of S prime, say I have square root of 2, e, pi, these irrational numbers. Okay, just like I have the group A of S, I will also have the group A of S prime. This set also has 3 elements, this set also has 3 elements. Here also I will be looking at bijections defined on S prime and also taking their values on S prime. Clearly these 2 groups are different because you see the functions are different. If you look at the function, say this function -1, 0, 1, -1, 0, 1, that maps -1 into -1, 0 into 1 and 1 into 0. Okay, this is a function in let me just give it a name also, f1. Say f1 is in A of S, and on the other hand we have a function that is like this. And this is, say, f2. Now f2 is a function in A of S prime because it's a bijection on S prime. f1 is a bijection on S. Can you say that A of S is equal to A of S prime? Obviously not, because can you consider f1 to be a function on S prime? No, it is not a function on S prime. Domains of f1 and f2 are different. Domain of f1 is S, domain of f2 is S prime. They are not just different, they are disjoint. There is no question of having f1 equal to f2. Although the functions look quite similar. I mean, if we are arranging these elements in the domain in a certain order, then the functions seem to be doing a similar kind of thing to the sets. But still, we cannot say f1 is equal to f2. They are not equal. Strictly speaking, they are not equal. So how can these 2 groups be equal? But then you say, of course they are not equal. So what is your point? And my answer to that query is that if these 2 groups are not equal, then what is S3? S3 by definition is the group A of S, where S is a set with 3 elements. But which set? That there is no mention of that set. So should I consider S3 to be this, or should I consider S3 to be this? And also, if you take another example of S, it can be any element in the universe of sets with 3 elements of its own, say S double prime. Then technically A of S double prime is yet another group, strictly speaking. So should I consider S3 to be this one? Then this notation itself seems to be problematic. And at this stage, if I don't say these things, it is problematic, which is one problem with Herstein's presentation. But given that the student, a beginner, will not look into things that subtly, it's not that much of a problem, but strictly speaking, it's a problem. What is the so then what do we do? How do we address this problem? Clearly we cannot we don't have, for a given n, we don't have a single Sn, but infinitely many Sns. You keep changing that underlying state S, you get different symmetric groups of degree 3, strictly speaking. But later you will see that there is a way of identifying two groups which may look different, but actually they are not different. At this stage, that I cannot say anything more on that although this A of S and A of S prime, A of S double prime, whatever S double prime may be, although they are strictly different groups, as groups they are not equal, but they are similar. In what sense, that we will see later on when the proper time comes. This similarity is somewhat like congruence of two congruent triangles which look exactly the same, have everything about them same, corresponding sides are equal, corresponding angles are equal, but strictly speaking they are two different triangles because they are different. This is one triangle, this is another triangle. But you see, if you study about this triangle, do you think you will have anything unknown about the second triangle? Clearly no, because everything is identical, so it's enough to study only this triangle and not the other triangle. There is no need to consider all the other congruent triangles, wherever they may appear. Only one triangle is enough. It's